So hello everyone, welcome back to Algo Daily. In this particular video, we are discussing LeetCode daily problem of the day, course schedule 4. And in this problem, we have to given a num courses, and the courses you have to take labeled from 0 to n-1, and you are given an array of prerequisite, and the prerequisite of I is equal to AI comma bi, and we have to given a in and that indicates that you must take course A of I first if you want to take course of B of I. And the example is 0 1, and then first we have to take 0, then we have to take 1, and now after that we have to return the answer array of answer, where answer of J is the answer of jth query. And now let's look at their problem statement. Then we have to look their example test cases and their coding implementation part. And so here in this problem we have to given a num courses. This num courses is basically the total number of courses with labeled of 0 to n-1, and after that we have to given this prerequisite. This prerequisite is a list of the course pair. This course pair is A comma B, and it indicating the course A must have to complete before course B. Like first we have to take this course A, then we have to take B, and this means like we have to indicating the course of A. This course of A must be completed before this course of B. And now the third we have to given one second this query, and this query is usually a list of query, and this is containing U and V, and where each query you must have to determine whether course of U, this course of U is prerequisite for course of V. Like first we have to course of U, then we have to jump on course of V. And after these operations we have to given the answer. The answer is usually for we have to return the array of where each value corresponds to whether the query is prerequisite relationship or not. Like we have to also identify what is prerequisite. First we have to take A, then we have to jump on B. So this is the relationship of prerequisite. So same thing for here, we have to return the array where each value corresponds to whether the query is prerequisite relationship is not is made a prerequisite relationship or not. We have to return true and false. And now let's look at their constraint. So that so these are our constraint. So in this constraint, first we have there 2 less than is equal to n less than is equal to 100, so that the number of courses is moderate. Here we have to moderate, and this moderate courses, so we can handle like up to O of n cube solution. It might be feasible for this solution, like 2 less than num courses less than is equal to 100. And same thing for here, we have this one, and this one is also prerequisite representation of directed graph, and sorry, directed edges with a maximum of all possible pair of courses. So that's why we have to given this one. And now after that we have here AI not is equal to B of I. It is a self loop. Self loops are not allowed for prerequisite. And then we have there this query, and this query is can be large, so pre-processing the graph efficient is critical. Like we have to use O of n cube solution, we have also discussed here. So queries can be large, okay, and then we have to given UI not is equal to V of I. So now let's look at their example first test case, so that you can understand how actually we work. And so in this example we have their num courses of 2 and this 2, and prerequisite we have to given 1 comma 0, this 1 comma 0, and this is the graph representation of this one, like 1 is connected to 0. And after that we have to given a query. This query is generally 0 comma 1 and 1 comma 0, and like here 0 comma 1, this 0 comma 1, there is no any connection, and so that's why this returns false. And so 1 comma 0, 1 comma 0 is connected with 1 to 0, so that's why we have to return true. So answer is false comma true. And same thing for second example. So in this example we have their num courses is 2 and prerequisite is empty, and then we have query is equal to 1 comma 0 and 0 comma 1. So in this example the prerequisite is nothing, so prerequisite is not exist, and also each courses is independent for like query 1. This query 1 is like 1 is not a prerequisite for 0, so that we have to return false. And same thing for query 2, the query 2 is 0 is prerequisite for 1, and then output is false because these are not present on our prerequisite form, and the query is generally we have to given 1 comma 0 and 0 comma 1, and so that's why we have to return false comma false. And this third example we have to given this 3, and the prerequisite is we have to given 1 2 1 0 2 0, and here we have 1 0 also given here, and 1 2 is also given here, and this 2 comma 0. Okay, and now we have the query of 1 comma 0 and 1 comma 2, this 1 comma 0 and this 1 comma 2. So now what we have to get here, 1 comma 0 we have a valid path, so that's why we have to return true. And so 1 comma 2 is also be connected here, and so that's why we have to return true. So after all these operations we have to getting true comma true, so answer we have to get. And now what we have to use for this algorithm to find efficiently, like we can use a 3 for loop I, j and k. So iterate with all over the nodes or all over the prerequisite, so that's why we have to find this one. So this is a brute force solution. And so after optimization what we can do here, you can also be do a DFS, BFS and many more algorithms for to finding their path and which uniquely identify. And now let's look at their coding implementation so that you can understand how actually we work. So this is my DFS function, and in this DFS function I actually use for first we have to mark current node as visited, and after that I have to traverse all the adjacent node. And here this case is if not visited, then we have to continue our DFS. Okay, so this is a simple DFS code for 3 lines. Like what we have to do, we have to first mark, and then we have to iterate with their adjacent node, and then if we have not visited, then we have to iterate their DFS. And after this we have I have to create an ordered map of adjacents, and I have to create it here the adjacency list to represent their prerequisite, and this is our list of adjacency, and this answer is our result array. And this vector of vector int arr, this arr is actually memoization for query result. Okay, and then what we have to do, we have to build a here we have to build a adjacency list, and then we have process each and every query. And then if query is not processed, like first we have there a, then b, and then c, and so on like this. So here we have to same thing we have to performing here, and then we have there a visited array of DFS, this one, this visited array of DFS, and then after performing all operation we have to here DFS perform from uh, DFS perform from source node, and then this query of like ARR of query of I0 is equal to visited is generally for cache result, and then after that we have to add into our add query result to answer. And this is a simple code for iterate all over the values and how we performing their values, and after that uh, we have to call DFS for when we have to iterate their queries and their prerequisite and so on things. Now and look this one, like this DFS is actually work on this DFS is uh, perform the depth first search to mark all reachable nodes from the starting node starting to reachable nodes, and then we have to mark visited, and then we have to recursively traverse adjacent node that haven't been visited. And so these things are like we have to pre-compute, then we have to visit, then we have to pre-compute, then we have to visit. So these are our operations for like follow up, and after this we have to create a adjacency list. This adjacency list we have to construct a directed graph representation of prerequisite, and after that we have their memoization. This memoization array, this memoization ARR store the result of whether one course is reachable from another to avoid their redundant calculation. Like when we have to calculate before, then we have to again not calculate. So this is our memoization result, and after that we have to pre-process our queries. We have to pre-process our queries. For each query we have to check if the result is already computed with ARR. If not, we have to perform their DFS from the source node. It is a simple iteration based code and implementation part and DFS part. So now let's look at their time complexity, and then we have to look their space complexity. So the time complexity of this code is we have to build a graph. The graph build of prerequisite is O of E time, and E is our number of edges. Okay, number of edges, and then we have their DFS. This DFS is generally O of V plus E, and where V is number of courses. This is our courses, and each query we have to initiate a DFS from its source node, and after that we have third thing is query processing. This query processing is taking O of Q time, and this Q is number of queries, and here we have, okay, this one. And now total time complexity of this code is O of E plus Q into V. Okay, so this is our time complexity of this code is O of E into, sorry, E plus Q into V, and then the space complexity of this code is we have their adjacency list, this taking O of E time, and visited array is taking O of V time, and the memoization array is O of V square, and the total space complexity of this code is O of V square plus E. So I hope you understand the logic and the implementation part, like how actually we have to iterate with this DFS, then we have to look their memoization part of ARR, and then we have to memorize all the codes and all the information from their queries and their prerequisite, and then we have to uh, perform their DFS from source node, and then we have to push into our answer. And I hope you understand this example test cases, like this num courses, this prerequisite, and this query means, like how we achieve these values. And so thank you everyone, thank you so much.